Hello! So, in this video we are going to cover a theorem, but almost arguably more important than the theorem is the technique used in the theorem. So this is a incredibly common sort of fundamental tool in the toolbox for mathematical proof. It's called the 3 epsilon proof. So the theorem is, suppose fn from R to R, suppose this is some sequence of continuous functions, and suppose fn converges to a function g uniformly. Then we can conclude g is also continuous. This is saying that unlike pointwise, which we've seen, convergence, uniform convergence, preserves this property of continuity, right? If all the fn's are continuous, then the g will be continuous if you have uniform, if it's a uniform limit as opposed to a pointwise limit, okay? All right, so I'll point out the 3 epsilon idea as we go, and hint, hint, this is almost always, really is always on some exam somewhere when you encounter it in your first sort of intro analysis class, so expect this to show up somewhere. Maybe not this proof, but the proof technique. All right, so we have fn, it's a sequence of continuous functions. So we have that fn converges to g uniformly. So ultimately we want to show g is continuous. So let epsilon greater than 0 be given. And fix x naught in R arbitrarily. The idea here is if I can show g is continuous at x naught, because x naught was fixed arbitrarily, it'll be continuous at all the x naughts, i.e. it is itself a continuous function, okay? So since f converges to g uniformly, there exists capital N so that if little n is bigger than capital N, then f of x minus, fn of x minus g of x is less than epsilon for all x and R. So here I'm not using x naught yet. I'm just saying this is true for any x at all, right? That's the uniform idea. If I only needed x naught, I could get away with pointwise, but we've seen that's not true, right? So this is just writing down the definition, only here is where the epsilon over 3 comes in, or the 3 epsilon proof comes in. I'm going to do, instead of epsilon, epsilon over 3, okay? And you'll see why when we get there. All right. So this is true just because this is the definition of uniform continuity, right? So I'm going to actually say that. So strictly speaking, the definition was that I gave was strictly greater than, but I could just pick an even bigger capital N so that it works that way, right? So I'm going to do that. So in particular, then f capital N of x naught minus g of x naught in absolute value is less than epsilon over 3. Right, so if I pick the capital N big enough that it works even at capital N, then I'm just replacing that, and it works for every x, so in particular it also works for x naught, okay? Now, since f capital N is continuous, now it's continuous everywhere, right? Sequence of continuous functions. Specifically, it's continuous at x naught. There exists delta greater than 0 so that if x minus x naught is less than delta, then fn of x minus fn of x naught is less than epsilon over 3. So far, it seems like I'm just sort of pulling this stuff out of the hat, right? Like all this stuff is true by the definitions that we have, but there's some question as to why I'm doing what I'm doing. And like a lot of the sort of classic and fundamental proof techniques, I am now going to pull a rabbit out of my hat because I am actually, believe it or not, done. So, by which I mean I have one line left to write to demonstrate that I'm done. I'll point out though, that I now have 1, 2, 3 epsilons that have shown up, and that's not a mistake. So, thus, we have, I'm going to have a long string of equalities / inequalities. So remember, our goal is to show that G is continuous at x naught for an arbitrary x naught. What does that mean? So I'll write this for x minus x naught less than delta. So we want to look at g of x minus g of x naught. And we want to conclude this is less than epsilon, right? But what's with all the f n's, f capital N's, all the craziness, right? So here's where the genius comes in, the rabbit out of a hat moment. I have g of x. I don't know how to relate it to g of x naught, but what I can do is relate it to f capital N of x, because I know something about how those are related, right? But I can't just add it on, right? I can't just subtract it off, I should say, so I have to add it back on. But now I have this piece, like I could relate those two, but now I have this thing sitting around, and I don't know how that's related to that. But what I can do is relate this to fn of x naught. And again, I can't just subtract that for free, so I have to add it back on. And I still have the minus g of x naught at the edge there. So I've added and subtracted 2 terms to get a total of 4 terms, because I added both and then I subtracted both. So I went from 2 things to 6 things. How could that be better? But herein lies the magic. This, by the triangle inequality, triangle equality says I can break this apart by putting pluses in between absolute values, right? So I have g of x minus fn of x plus fn of x minus fn of x naught plus fn of x naught minus g of x naught. Now, according to this, as long as n is at least capital N, which it is, fn of x, the distance between fn of x and g of x, is smaller than epsilon over 3. So this thing is smaller than epsilon over 3. Fn of x minus fn of x naught, well, as long as I have it within delta, which I do, this is less than epsilon over 3. And just like before, this is true for every x. In particular, it's true for x naught. But epsilon over 3 plus epsilon over 3 plus epsilon over 3, that is epsilon. So g of x is continuous at x naught. Thus, g is continuous. So the whole thing about this is that the 3 epsilon proof, the whole idea is that I need to add 0 cleverly, but it's not immediately obvious because there isn't one thing that I can relate to both this and this simultaneously. And so this is why it's sort of a fundamental tool, is that instead of coming up with one thing that works on both of these at the same time, you come up with one relationship as a lever to go between a related thing and a related thing, right? You know something about fn x minus fn x naught, where one of those, the fn x naught, you can relate to g of x naught, and the other one, fn of x, you can relate to the g of x. So you sort of inject this sort of middle pivot point in order to give you the other pieces to relate to the pieces you started with. Right? So this is the idea of the 3 epsilon proof and why it's so useful. Aside from that, aside from the technique, this is also incredibly useful because this tells us, as we sort of mentioned before, that uniform limits, if I converge uniformly, then I get to preserve continuity, which is an extremely helpful property, generally speaking. Okay? So that is that.